so hi everyone. Thanks for having me here. I will just add one thing to the introduction, that I'm a PhD student of both University of Warsaw and IC for the Institute of Photonic Sciences in Barcelona. And my supervisors are, as Professor Tippenbach said, Dr. Michał Tomza, who's here today, and as well as Professor Maciej Levenstein. My aim for today's talk is to explain the work I did under their supervision, which aims to answer the following question. So, what interesting physics can we gain when putting into the trap, in the one-dimensional trap, two ultracold molecules? It turns out that the answer is pretty complex, and it's a result from the fact that these molecules have pretty complex internal structure, and also their interactions are not so trivial. So, and when we add the external fields to the picture, it gets even more convoluted. But I definitely want to lead you through this work smoothly, so I will start slowly, of course. So I will begin with description of the promises that molecules bring into the field of ultracold physics. Also the experimental work that was done already with ultracold molecules. Then I will discuss the Hamiltonian we use to describe the system, and highlighting the differences between the atomic and molecular system to really guide you what to do if you want to analyze, if you maybe want to analyze a system that was so far atomic in your theory work, and now you want to replace the atoms with molecules, and so really guide you what you need to take into account. And then I move to description of chosen results contained in two papers that we published on the way. These results focus on the impact of the anisotropic interaction on the spectrum and other properties of the system, and also the magnetic properties of the system, how can we control them. And finally, I will show you two quench dynamic setups, and I will explain why we want to study this quench dynamics, but slowly. I mean, I will get to it. And finally, I will conclude with our plans and outlook and possible extensions of the system. And in the end, I hope you will see why it's worthwhile to play with molecules instead of atoms. And before I move on, I just want to really encourage you to ask questions during the talk, and please feel free to interrupt me at any time. I'm happy to answer all the questions. Okay, so let's start with the state of the art and our motivation. So we all probably know that ultracold atoms in optical lattices have already proven to be a very versatile tool in quantum many-body physics. With ultracold atoms, we were able to experimentally study the quantum transition between superfluid phase and the mode insulator, or study magnons that appear there. They with really amazing experimental tools like quantum gas microscopy that has the resolution on the level of single spins and single side densities. We are able to really build great atomic setups with high precision. We were also, and what is really exciting, we are entering the moment when really the experiments can test hypotheses which are maybe currently unavailable for theory. So for example, it was shown in this experiment here that two-dimensional many-body localization takes place, for which, as far as I know, there were not so much theoretical proof provided so far. So there are many works being done with ultracold atoms. We want to build on that. And besides of this quantum gas microscopy that allows us great like detection skills, we can also really control the systems on at the single particle level, thanks to the tool that's called optical tweezers. And what is really cool about this tool is it doesn't have really huge requirements, especially regarding the temperature. It doesn't have to be, you don't have to have ultra cold particles to trap them really in a single space. That's why it started to be really popular also in biology, and research really came flowing in this direction. But also in ultra cold physics, it proved to be very useful tool. And with really this single atom precision, people are able to build very complex, also three-dimensional systems out of atoms. And so, as you see, very different geometries are possible, like including Eiffel Tower. And it was shown, and manipulation is surprisingly manageable. So this is also hope for molecules for the future. And yes, so we have this quantum microscopy, we have optical tweezers, we have great control over ultra cold atoms.
Excuse me, so that that manipulation in these figures was basically, you know, addressing each atom, and they were all guided by the tweezers, or this was some kind of geometrical structure that trapped them?
No. Actually, you first trap them in the optical tweezers. Sometimes if you trap more than one atom per tweezer, you have to get rid of that. And then you have this really single atoms in optical tweezers, and then you move them slowly. As far as I'm concerned, Michał can correct me if I'm wrong, but yes. So you manipulate it like after that. So this is amazing.
Yeah.
Okay. So okay, so we know that already. It's shown really convincingly that ultra cold atoms are powerful too. But we want to have even more power. So let's analyze what happens if we replace atoms with molecules. The most important things that we need to take into account is the fact that they have very different interactions. So between atoms, the interactions are mostly isotropic and short range. While with molecules, you have to take into account the structure, the orientation. So they are anisotropic, and they are also long range. Apart from the magnetic dipole moment, they also have electric dipole moment. I mean, they may have if they are polar, and they have much more complex internal structure, including rotational and vibrational structure. And also, like, you get this for free. It can be curse or it can be blessing, but you have many couplings between this internal degrees of freedom. You can use it to your advantage, or you have to get rid of them if that's problematic for you. So they are more complex. They give you more power, but they also are more demanding when in handling. Okay, but the promises they bring, they're pretty interesting. So first of all, they promise a toolbox for lattice spin models with topological order. So this would be really nice to have a fully controllable molecular systems with which we can really study topological models. And there were many proposals that with rotational states, which are coupled by microwaves, they both can encode qubits, and so we can have some gates built on them, but also they can be used to simulate quantum magnetism models. So this is another direction people are moving in towards. Also, there were proposals that showed that they can really simulate polarons, and they were shown to have there are like rich phase diagrams that can be reached with ultracold molecules coming from their dipolar properties. So and already they were used in the proposals I told you a moment ago was mostly from the quantum many-body physics field, but they are also used in ultracold chemistry, which really studies the quantum effects that play role during the chemical reactions at the ultracold temperatures, and also used for precision measurements thanks to this internal degrees of freedom. There are more of them. They can be used, for example, in a daring quest of determining the value of electron-electric dipole moment, which can be then used to cancel some hopes regarding some alternatives to standard model theories, because they have some limits for this electric dipole moment, and so far we are finding possible maximum value and pushing. So yes, so this would be the promises and what we can gain out of molecular properties. But what about experiments? I told you already that they are more demanding when handling, but it's been tackled right now actually. So we can people already can build really like arrays of polar molecules, polar ultracold molecules in their ground states, using exactly optical tweezers. So this bottom-up approach, it was used so far in two groups on two different ultracold molecules. So you start with trapping atoms in this optical tweezers. You really make sure that they are cooled and they're in ground states, and you have one atom per one optical tweezer. Then you merge these optical tweezers, you get the weakly bound molecule, and in the end you can transfer this weakly bound molecule to the ground state. And you get, so in the end you have an optical tweezers with really single ground state ultracold molecules. This is pretty awesome. I think that this approach is like people are connecting the largest hopes with. But there's also another approach with which you can create this many-body system, and it's like kind of opposite way. So you start with forming the molecules, then you laser cool them, and then you load them to traps. And this approach was used in this collaboration by Dawid-Łękowska with calcium fluoride. Okay, so I hope I convinced you that both we can really gain interesting stuff from molecular setups, and that the setups are maybe not really accessible, but they are really close. I mean, there will be people are working on this right now, and amazing results are already provided and on the way. Okay, so let's move to with this introduction, we can move to what we've really done. And so I will start with this kind of like method section. I will describe the Hamiltonian and what parts are really coming from the molecular properties of the system. And I will start with with one slide that shows a seminal work from 1998. It's the work on two ultracold atoms in the one-dimensional harmonic trap. This is let's say our starting point. And you see that, and the result you see is an energy spectrum of such a system. And I wrote down the Hamiltonian, so we have the idea of what's different here. So here we have the part describing the trap and the part describing the isotropic interaction between these atoms. So what happens in our model? Our model, we still get the trap because it's the same kind of trap. We have, however, also the part of the Hamiltonian describing the internal structure of the molecules. I will soon talk about what parts we take into account. Because we want to further control the system, we analyze how the external fields modify the response. And then we have this interaction part, which in atomic case is only this isotropic interaction. To solve this Hamiltonian, we use the exact digitalization with the basis set consisting of the harmonic oscillator functions, the quantum rigid rotor eigenfunctions, and the spin eigenfunctions of both molecules. Yes. So, and we are able to write down this Hamiltonian in this basis that we know the form. Okay. So the trap is only the quantum harmonic oscillator Hamiltonian, nothing too fancy. With this molecular part, it's still pretty easy, but there is like, let's say, the main meat from the problem coming from this part. So to molecular structure in our case is a rotational structure. So we model each of this molecule as a quantum rigid rotor, and they have a rotational structure coming out of this rotations, out of possibility of rotations. There is also an intrinsic coupling between the rotation and electronic spin. So each of this molecule has a spin rotation coupling between its individual electronic total spin and its rotation. And this will prove pretty important. The strength of the spin rotation I label as gamma. With the field, it's pretty simple. We have the external electric field and external magnetic field, and we described this their effect via Stark and Zeeman effects. So this is all pretty basic. Okay, and the most let's say non-trivial part. So apart from this, so this is the interaction part of the molecule. We want to describe how they interact with each other. So apart from the isotropic part, which is identical as in the atomic case, we also have anisotropic interaction, which will prove very crucial in the further results. So please bear with me for a second. You can imagine it as a way of coupling the rotational states. So this part, so this anisotropic interaction can exchange rotational momenta between these molecules, and this is how it's easier to it's the easiest way to understand this anisotropic interaction. Okay. So that's the Hamiltonian. Do you have some?
And what physically, what's the nature of this interaction for you? Is it dipole-dipole?
I would say it indifferently. Dipole-dipole interaction can be also. I mean, we can encode it with this kind of operator that flips rotational momenta, but dipole would have different conditions about how many rotational states it can flip, and like by how many rotational angular momenta, like quanta of momenta is exchanged. So it has this nature of dipolar interaction, but it's not exactly dipolar interaction. It's we could we also included the dipolar interaction. It would be like another term. But
okay, so I come back to my question. So what's the origin of this interaction?
So you can if you like draw the potential between molecules, like chemically driven potential between molecules, you can see that there is the dependence on the orientation of these molecules, right? So
spin is a spin of the molecule in this.
Sorry, no, it's
spin, or atomic spin.
Hold on.
May I say something?
Yes.
You know, at the very end, you've got a couple of charges which are, of course, bounded in the molecular situation, and all the interactions are, of course, electromagnetic. And as we know, we all know, electromagnetic interaction can be set into the system of parts, yes, electric dipolar, magnetic dipolar, quadrupole, yes, and so on. So sure. What sort of interaction, electromagnetic interaction, you have in mind with this term?
Okay, I know what you mean, and I actually didn't I wasn't thinking about this interaction in this electromagnetic way.
I mean, this is the same interaction that is isotropic interaction between atoms, but because molecules can have orientation, so orientation dependence of the electrostatic electronic interaction gives this coupling between different rotational states. So this is effectively just the electronic structure dressed already in rotation.
Okay.
The anisotropy of.
Okay, so it's electrostatic part, the combination of the. Okay.
So you don't have to you don't have to expand it in the moments, right? I mean, it doesn't have to be dipole. It is all included somehow in this proposal.
Well, of course, there is an effective way when we are talking about interatomic or intermolecular potential. That I agree. Yes.
Yeah.
But still, the origins should be clear, and I think what Tomza says is explaining.
Yeah. Thanks. But thanks for the question, because it turns out I didn't think about that. So thanks for that.
Is it? This is all linear, right? I mean, there's no spin changing interactions and something like that. This is linear Hamiltonian, right?
Oh
no, because there are interactions, so it cannot be linear.
yeah, I mean, so I would say that so linear in what sense? I mean, there can be okay.
Two particle. I mean.
Yeah. So there can be spin exchange, but not directly from this term. This term switches the rotational states, right? But for example, this part is couples the electronic spin and the rotational states, so it can be like indirectly happening.
Okay.
That doesn't answer your question.
Yes. And can be also like higher order Zeeman effects and.
Sure. But actually, we found out that it's already pretty complex, and so we start with basic effects.
Thank you.
Okay, but thanks a lot for the questions. Okay, so before I move on to the results, I'd like to discuss one thing, namely the role of this rotational constant in the model, because actually it turns out that it in the first approximation really determines the importance of the molecular structure in the problem and why. So you have this this plot here shows you the energy spectrum, but energy is in the rotational constant units. And here you see the ratio between the rotational constant of the molecules and the frequency of the harmonic trapping. So as you when you have a trap and you have the rotational structure, you see that we get these two degrees of freedom, and each of them has its levels, and a lot of things changes if you have if the ratio between the rotational structure and the frequency trapping frequency is small, then when it's large. If it's small, then like before you encounter next harmonic level, you have many rotational states. So all the physics that are coming from the molecularity of the system is really enhanced. If you have on the other hand the ratio that is got like 50 in 100, much bigger than 1, you see that you have a lot of harmonic harmonic levels before you reach first rotational state. So basically, rotational states are much further apart than harmonic levels. So actually, it's more similar to atoms than in harmonic traps in this sense. So in a sense that rotational structure gets less, it's less pronounced, less important in the problem. So what we did in the first approach, we chose pretty small rotational constant, so like ratio between rotational constant and the harmonic trapping, which allowed really to enhance this molecular features. And it was kind of a toy model that we wanted to, with which we wanted to show what can we expect from the molecular properties of the system. And on the other, and then we get a little more realistic, and we chose a larger ratio that, as you see, allows few rotational states before we encounter the harmonic trap level. And sorry, no, actually we have a free harmonic trap levels before we encounter one rotational state, but it's still not so further apart. However, it's really important to know the typical experiment. So if you have ground state molecules in a harmonic traps, the ratio is much larger than 1. It's more 100 or even 1000, because the trap frequencies are around 1 kilohertz to 1 megahertz, and the ground state molecules rotational constant are around hundreds of megahertz. So if we'd like to really realize the system in reality, we would need to use the weakly bound molecules, which have much higher rotational constants, much lower rotational constants, and very tight traps. But it's possible. To be completely fair, I would say it's on the verge of being possible. But it's realistic, I can say. We checked that for our last paper. Okay, so with this, do you have some more questions? Because if not, I would move to the results.
Can I come back, because I have a so tight trap is omega big, right?
Yes.
So when omega so when omega is big, the spacing between levels is big.
Yes, between harmonic.
So then you can have many rotational levels before you encounter the next trap level.
We would like to have that, but it's never possible. I mean, we can have
but experiments are actually, so experiments are when B is big and omega is small.
Yes.
So you have quite a few trap levels before you actually change your rotational level.
Yeah,
right?
exactly. That's why actually, okay, I won't click because it will take a moment. But if you remember, I said that for using molecules as qubits and for modeling quantum magnetism, people use rotational states dressed in microwave fields. This is why they needed this additional coupling to make it really visible. So there are also tricks to make it visible, even though it's like very far away. But yeah, we wanted to like have a large omega, small rotational coupling, weakly bound molecules, and this tight traps. So this is how we can get into this regime.
Thank you.
Okay. So regarding the results, it's just chosen results. In the end, I will show you the like references. If you're interested, please go there. I will again just remind you the result for the 2 atoms. To like introduce one concept that probably you all perfectly know, the Tongue-Girardet regime. It takes place when 2 atoms are really strongly repulsive. And I just wanted to tell you about that because we can have this regime as well in molecules with some conditions. Okay, but this is energy spectrum for 2 atoms, and I would definitely not go. I mean, I made this mistake once. I won't go through energy spectra because this is in molecule case because this is I mean, this is very like modern art. But I will just show you one set of energy spectra. Okay. And this is because I really want to show you the impact of the anisotropic intermolecular interaction. So this part that Professor Żurzewski was asking about. So now, like we have we have this trap as in case of atoms. We have this isotropic interaction as in case of atoms, but additionally we have rotational states, and we have this anisotropic interaction. And these are energy spectra as a function of anisotropic interaction. And what I just want you to notice in this picture, okay, it's dense, so this is one thing, but it's obvious. What is the main message from these pictures is that anisotropic interaction brings down states with high rotational momenta. So look here, the colors get like blue is total rotational angular momentum 1, green is 2, yellow is 3, and so on. So you see how crazy it gets. And
could you please spell out what are the constants of motion in your case? In other words, how many quantum numbers do you need to label the states?
Sure. So we have n labeling the quantum harmonic oscillator states.
Yes.
We have actually maybe I will. Okay, if you can give me one. Okay, I have the this is n. J is total rotational angular momentum. So this is coming from the summing of rotational angular momenta of one and of first and second molecule. We have this projection of this total rotational momenta, mj. And
yes.
And so far for this anisotropic energy spectra, we have just these five quantum numbers. But then when I will move to magnetic properties and quench dynamics, we'll also get spin of each molecule plus the projection of each of the electronic total spin.
Okay.
Okay.
But some of them are coupled and mixed, right?
Oh yeah. What I mean, this is our of course our basis set. So in this case, J is a good, the total rotational momentum is a good quantum number along with the M. So J1 and J2 are coupled because
sure.
from the entropic molecular interaction. And then with additional Hamiltonian parts, things get coupled a lot. Okay, so coming back, we have this, the interaction, intermolecular interaction pushes down states with high rotational angular momenta, high J. This is one message from this. And secondly, if you see, so this, if you look closer, so this is the plot for the same, as a function of the same strength of the anisotropic interactions, but they differ with the isotropic interaction. So here is 0, and this act of the anisotropic interaction is the fastest. Here it's 4, and it's like in the middle, and then it's infinite, and it's even slower. So the message is they compete with each other. The isotropic and anisotropic interaction. And but here we see that we can also have this Tongue-Girardi regime as long as the isotropic part is much stronger than anisotropic part. So this was the main message I wanted to convey to you. And regarding this state with high J going down with anisotropic part, we can therefore have a ground state that has a non-zero total rotational momentum, and it of course depends on the interplay of these two strengths of the isotropic interaction and anisotropic interaction. Of course, the larger anisotropic, the larger, the higher J you can get as your ground state. So this is one message. This is a very short one. Another thing is that you can, when we turn on the external electric field, suddenly we have also mixing of the J's. Only M stays as a correct quantum number, and because of that and coupling of the states, we can really see that we can pump the rotational angular momenta into the system with external electric field. So the message from here just is that with electric field we can control the rotational properties of the system. Okay, this is another building block of our story. Okay, so now we get, so far we haven't really considered the magnetic properties. So we ignored the spin. Now we turn it on. So like now we think about electronic spin. So it's so suddenly we can analyze the Zeeman effect, but also the effect of the spin rotation coupling that I told you it's important. And if we look at the magnetization of the system, so the sum of the projections of the electronic spins of both molecules, we can draw the magnetization diagrams and analyze how these properties, so anisotropic interaction and spin rotation coupling, impact the response to external fields. And we can of course draw these phase diagrams for any properties we want, but we noted, we played with that a lot, and we noticed that spin rotation coupling and anisotropic interaction strength has the most important impact on the response. So first of all, so this upper row, it's spin 1/2 molecules, and the lower row is a spin 3/2 molecules. So first obvious observation is that a number of accessible magnetizations depends on the electronic spin of molecules, of course. But what is less trivial? So the most basic mechanisms going between this change of magnetizations in the system is of course just Zeeman and Stark effects. So if we didn't have any anisotropic coupling and the spin rotation coupling, we would have something like this. It would be something like this plot. So for the larger magnetic field, the faster we have this negative magnetization, and it's countered by the Stark effect, but not so much. So, but what is interesting, first of all, the transition between these two states, two magnetizations, is determined by the strength of the spin rotation coupling. So the larger spin rotation coupling, the more smooth the transition is. But also, it turned out that the anisotropic interaction plays a role, and it's the easiest to see here in this force 3/2 spins, where we see that all these columns are for strong anisotropic interaction strength. We see that we get additional magnetization values accessible then as compared to the diagrams with medium anisotropic part. Why? Because, as I said before, the anisotropic interaction brings down states with high rotational momenta, and because of that, it allows additional magnetization values. So that would be the two most important messages from that. And of course, the fact that we can really control the magnetization with an external electric field. It's also nice because always this coupling between electric and magnetic properties can be useful for experiments or for doing interesting stuff, interesting simulations. Okay. And so I keep saying about spin rotation coupling and the anisotropic interaction strength. We identified it as the most interesting and important molecular properties in the system. But getting them finding their values isn't something we well know how to do. Spin rotation coupling is not easy to calculate theoretically, and as well as anisotropic interaction strength. So we came up with the proposal to extract them from the quench dynamic setup. So quench consists in the sudden change of some parameters, and I will tell you in a moment what parameters we want to change for which setup, for which molecular property. And after this sudden change of parameters, this quench of parameters, we see how the time evolution of the system looks like. And with the Fourier transform, we can get plots that show us frequencies governing this time evolution. And with such sets of data, we can, I will show you how to extract this molecular property from our system. Just, important remark is that our quench dynamics experiments are kind of are simplified. So in reality, of course, things would be much more complicated because all the molecular properties are coupled to each other. But in the first approximation, they would look as we show. So this is the small disclaimer. Okay. So if you want to extract how large is an isotropic interaction as compared to isotropic interaction, we can quench this two properties, so quench the interaction. We would, you can do it. I mean, the most, I think, realistic scenario would be quenching the trapping, because this, I mean, it was shown in the Professor Bush work that it's pretty analogous to quenching the interaction between atoms. So we hope that it will be analogous also for molecules. And so after quenching this, we can look at the cloud size of the system. So it experimentally it's complicated. I'm not sure how feasible it is, but let's focus on theory for a second. Then we can discuss whether it's feasible. And but if it's feasible, then it's a really good way of extracting these properties. Why? Because states are capped when we have only iso and anisotropic interaction. We have coupling between harmonic states, which are which are evenly spaced. So it's very easy to see in the Fourier transform version. Plus, there is an interaction with the ground state, and the ground state is very sensitive to the value of an isotropic interaction, which is, and it will serve as an indicator for us. So here we have the even iso and anisotropic interaction, and we have an evenly spaced ladder of frequencies, and now we have a growing anisotropic interaction, and we see that this peak that is getting separated from the ladder is exactly the one coming from the ground state, which is getting pushed down by an isotropic interaction. And here it's even further down. So this is really perfect indicator of how large anisotropic interaction is as compared to isotropic interaction.
So how those three figures differ? They have a different ratio of the
yes, of the anisotropic and isotropic interaction. So here they are even. Here is a little bigger. The isotropic interaction is a little bigger, and here is much bigger. So of course, if we were supposed to calculate it for a real system, we would need to put real numbers. So I think it's enough to say that it's a little stronger. It's a much stronger. But we see how this moves. This peak moves. So this is, yeah. I mean, we really like it. Okay. If that's okay, I will move to the how to extract the spin rotation coupling. And this is the quench of the electric field. So we have our system. We quench the electric field from 0 to 5. We have the same quench in both cases. What changes is the value of the spin rotation coupling here, which is small, and here is large. And we follow the magnetization changes in time after this quench. And I mean, it's much more complex now because if we follow the spin rotation, if we have a decoupling of spin rotation and we quench the electric field, we have many couplings governing this time evolution. But it's more. I mean, there is one really simple indicator of the spin rotation coupling strength here, and is the how strong or how large are these couplings here. There are two dominant couplings, and they can be really easily mapped to the strength of the spin rotation coupling, because as you see, there is this logarithmic scale. So yeah. So this is so the message from here is there is a single peak that that grows slowly with the spin rotation coupling, then it saturates, but it's also a nice indicator. Okay, so this is it. This will be the highlights of our results. I have still 1 minute left, so I will start with the summary just to briefly remind you what we were talking about. So molecular in our case means, and I think very general means, rotational structure, anisotropic interactions, and spin rotation. I remind you again that anisotropic interaction, the main thing it does is it brings down the states with high rotational angular momenta down.
So that when it brings it down, it means they are more.
It lowers energy.
Yeah, so it means that they are more present in the dynamics in the.
Yes, as well.
Okay.
I mean, but it's in the sense that we look at the ground state, right? So and then they are more present in dynamics. Yep. We also showed that we can control magnetic properties with external electric field, and we showed examples how quench dynamics can reveal the molecular properties of the system. And as I don't have much time, I will skip this one slide, but I think it's pretty interesting. But I mean, this is something I was talking about to you, that it is possible to make such a system with weakly bound molecules in a tight traps. But this is some extra thing. I mean, I welcome you to ask about it later. But I would just, so then I would just move to plans and possible extensions. So we right now are working with Marta Sroczyńska, Dr. Idzieszek, and Dr. Jachimski on the molecules and the tweezers, and how the harmonic trapping impacts the quantum gate encoded in the states. We also plan to play with the molecules in optical tweezers and change their geometry. And there's a few body system focused really on the magnetic and electric property of the system, and maybe follow the frustration. And finally, my final project will be the many body system of the molecules, and again focusing on this the interplay between magnetic and electric properties. And so thanks a lot for your attention.
Thank you very much.